Hello, this is the second from the last lecture for the ME4234 Dynamics of Control Systems lab. And then this lab is actually quite exciting when you get to see it in person. This is about a basic sided system, and then the system is a two-story building. One second. Okay, next slide. So basic static system, we've seen this before from ME3333 system and vibrations. And this is a system we have a single mass. It's connected to by a base that's moving. Okay, so in here y sub t is a prescribed motion and x of t is your output motion of the mass. It's a response of the mass. And then c is the damping coefficient and k is the spring constant. When you find the equation of motion, you'll see that this is m. You see the following equation of motion where the right hand side looks a little bit funny because the input is coming in as a motion. So if you divide everything by mass m, okay, you can not you can normalize the equation. It's not quite non-dimensional. You can normalize the equation so that c over m can be written as 2 times the damping ratio is zeta times the natural frequency of omega n, and k over m is the natural frequency squared. Okay, so next slide. The free or the natural response can be found by setting the right hand side equal to 0, and the response will be something like this. Assuming this is an underdamped system, we have some exponential decaying function that's multiplying the sinusoidal function with the what's called the damped natural frequency omega d. Okay? For the case of undamped system where zeta is equal to 0, you'll get x of t is equal to just pure sinusoidal function with a natural frequency of omega n. And the free response tells us various things, and then one of the most important things is the natural frequency of the system in the absence of damping. And in the presence of damping, you get to see the damped natural frequency and the damping exponential decaying envelope. Okay. So now the harmonically forced system, when you have a harmonic input, for this case, we have a harmonically moving wall, okay, that's prescribed by y sub t equal to some amplitude capital Y times sine omega t, where y is the constant number, okay, it's a constant amplitude, and omega is the input or the forcing or the base frequency. Now the response is given by the first part is the homogeneous solution plus now the particular solution. Okay? So when we have damping, the first part of the response, which is homogeneous solution, will decay to 0, and we only end up with a particular solution, and we call this particular solution steady state response because it persists. Okay? As the time goes to infinity, this part of the response will still remain. So going back to the original equation of motion, how do we find the response amplitude, capital X, and how do we find the phase, phase of the response with respect to the input? Okay, so we usually assume the input has no phase. Okay, so whatever we find, this phase phi here is the phase with respect to the input. Okay, so we learned this in ME3333. That we can find the particular solution using a transfer function. If we didn't have this tool, if we only had differential equations, just the math course in differential equations, then we will be assuming we'll just use the trial solution method where particular solution is equal to a times sine omega t plus b times cosine omega t, and substitute back into the original equation and find a and b. And that process is quite lengthy. Okay, this is actually a shortcut. Okay, I think this is probably one of the best things that came out of our course. So now we have a transfer function where the numerator is the right hand side of the equation, okay, and the denominator is the left hand side of the equation after Laplace transform has been taken. So t sub s is x sub s divided by y sub s. Yeah, it's the output over input. So the capital X, which is the amplitude of the response, is the amplitude of the input displacement, capital Y, times the transfer function evaluated at the forcing frequency times I, where the S is evaluated, the I times forcing frequency, input frequency, and then phase V of the output. Okay, output is the angle of that the transfer function, and then when you evaluate S at I times omega, the transfer function will be a complex number. So you only extract the absolute value to find the amplitude, and you find the angle, okay, of the complex number to find the phase. Okay? So for example, okay, if you don't remember, let's consider a system, just a made up system. So let's say you have mass is 1 kilogram, C is 4 Newton second per meter, and K spring constant is 5 Newton per meter. And then it's being excited by a y of t that has an amplitude of 7. It's a little ridiculous because it says it's 7 meters, okay, where the spring constant is like 5 Newton per meter. So anyway, pay no attention, okay, pay no attention to the to the unit for now, okay, just for now. So first you realize that this is an asymptotically stable system. That means you have a damping, and therefore your free response or the homogeneous solution will go to 0. So that therefore what's remaining, the particular solution that's sinusoidal, is the steady state response. So transfer function for this system is given by the 4s plus 5 divided by s squared plus 4s plus 5. Where did I get that from? So top is the right hand side, the plus of the right hand side, and the denominator is the Laplace transform of the left hand side, okay, where t sub s is x divided by y sub s. So continuing with an example, so transfer function is evaluated at the forcing frequency. So substitute s equal to 2 times I, and you have to be careful that it has to be in radians per second. So s is I times omega, where omega is really has been radians per second. So you substitute that in, and this number, okay, this complex number can be evaluated using your calculator. So I think there's an option called complex, and you find that the absolute value is 1.17 and the angle is negative 0.4342 radians. Okay, so now our steady state response is 7. Where did I get the 7 from? That's the input amplitude times the gain. So this is this number, the absolute value of the transfer function is called the gain, okay, times cosine, because it was being forced at cosine. Cosine times 2t, same as 2t, same of the input frequency, minus, okay, because the phase angle was negative 0.434. I chopped off the last two. So when you look at the response, okay, that's what it looks like. The input is the blue line that starts from 7 cosine 2t, okay, so this is a blue line, and then output, okay, output response looks like this, okay, a little bit raised. So just by looking at this plot, you should be able to tell the forcing frequency and magnification factor, or the control people like to call it gain, and the phase leg of the output response. How do we do that? So first we read the input amplitude, which is at 7 right here, and right here, and then we read the output amplitude of 8.19, and the gain is, well, I'm answering the second question first. Gain is the output amplitude divided by the input amplitude. So 8.19 divided by 7 will give you the gain. So now the forcing frequency, which is same as the response frequency, because remember that anything that has to do with the natural frequency, it already died out because this is an asymptotically stable system. So just look at the period from, let's say, from here to here, peak to peak distance, or you can look at the blue one, the peak to peak distance, and you'll see the period is about 3.14 seconds. Okay, and then the response lags behind. See, lags behind the input. Okay, so input has a peak first, then 0.22 second later, output will have a peak. So it has a time lag of 0.22 second that corresponds to the phase lag of 25 degrees, approximately 25 degrees. How did I calculate this? This is calculated by the following method. So what you do is you look at the fraction of the time lag out of the total period. So you have 0.22 divided by 3.14. So that's the fraction of the time lag out of the whole period. Now simply you multiply by 360 degrees, and that'll give you the phase lag in degrees. So let's see. Yeah, and then this result could have gotten, I didn't actually have to run the simulation. I didn't actually have to solve the differential equation. I could actually gotten this result using a Bode plot. So you do Bode, so you have to make sure you have a control toolbox. You write Bode and go numerator, comma, denominator. So this one says 4s plus 5, and the denominator is 1s, s squared plus 4s plus 5. Then what I did was I zoomed in at frequency of 2. How do I know this is 2? This is in logarithmic scale. It's a little inconvenient for me to read the values, so I had to zoom in a lot. So this is 10 to the 0th power, that's 1. Okay, 2 is the next mark, 3, 4, 5, dot, 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 this is 10. Okay, and then this right here, this value right there is now, what do you think it is? This is 10. What is this one? Remember, this is 100 right here. Okay, this is 20, 30, 40. Okay, that's how you can read the logarithmic scale. So anyway, I zoomed in and looked at this value, the magnitude in decibels. It's 1.30 decibels, and the phasing was negative 24.9 degrees. And the phase certainly agrees with what I got before, just looking at the time graph. So that was 25 degrees. Lag was lag, so that's why it's negative, meaning it's coming after, right? You have a shift to the right, so that means you have negative number. Okay, what is this negative number right here for the phase? Ooh, I lost my. Okay, right there. Okay, right there. So now 1.30 decibel. If you turn this into a pure ratio, how do you do this? You divide by 20 decibels, and you raise a 10 to the that number. Okay, so it's 10 to the 1.30 divided by 20, and you will get 1.16, which is spot on. Okay, when you divide the 8.19 divided by 7, you'll get 1.16. So now let's generalize. So how do we find the particular solution to harmonic inputs at any frequency? Okay, so I think all I did was I just didn't simplify. Okay, I didn't plug in s is equal to I times 2. I just plug in s equal to I omega. So that's your transfer function again. What happened? Oh yeah, that's your transfer function again, where this number came from I omega the squared. When you square I, you get negative 1. I'm thinking, I think I'm missing an I here. I'm definitely missing an I here. Okay, I'll fix that for the next time. So I'm missing I right there too. Okay, so for the Bode plots, if you don't own control toolbox, you can't use Bode command. So what you do is you can just use the regular MATLAB command. So look at that. I actually fixed my mistake. So you have I times 2 times zeta times omega n. Okay, and there's an I here, but I forgot my I there. So this is the Bode plots generated for many values of damping ratio zeta from 0.1 to 3 not equal interval. I think I used like 0.1, 0.2, 0.3 all the way up to 1. Then I went 1.5 to 2.5 and 3. Okay. For the input frequency ranging from 0 to 4. Okay, so one thing to note that I had to set the natural frequency to be 1. Okay, so right now the x-axis in these plots are forcing frequency assuming omega n is equal to 1, or another way to think about it is this is the frequency ratio. Okay, the horizontal axis is the omega divided by omega n. So this mark right here, when this is equal to 2, that means the forcing input frequency, not forcing, input frequency is twice the natural frequency. Okay. So what does it all mean? You have all this beautiful plot. What does it, what do they mean? What that means is, let's say you have input frequency that is near, okay, that is very near the natural frequency. So right now I put it at 95%. your forcing frequency is at 95% of the natural frequency. Okay, and I chose as zeta is equal to zero point 0.1, so this is a very lightly damped system. So when zeta is equal to zero point 0.1 and the forcing frequency is a 95% of the natural frequency, you have the gain nearly 5, okay, nearly close to 5, okay, that number, and the phase about 20 degrees or so. Okay. So when you look at the motion of the base, which is just sinusoidal function, oh, this time I had a change of heart. I'm using sine, it looks like. So, so you have this, you have a base motion, your base is shaking, unif- um, um, at the frequency of 95% of the natural frequency. Then what will happen to the mass? Look, you'll have it's the motion is gonna start growing and growing, and until and it's gonna you're gonna reach the steady state eventually. And when you look at the steady state amplitude, it's about 5 times. Okay, 5 times of the input frequency. Not only that, okay, it seems to be lagging behind slightly. Okay, it's a little hard for me to tell by how many degrees. Okay, but it's not. I know that's not quite 180. If it were 180, it should be all those two peaks should be it should be upside down. When the input is having a maximum, the output should be having a minimum. So it's not quite that. Okay, and lucky you, I actually have animation. Okay, so I figure I'll give you something that's a little exciting. So this is a case where when the natural frequency is 3 and the base frequency is 2.85. So this is exactly when the base frequency, this is the input base motion frequency is 95% of the natural frequency, and then zeta is zero point 0.1. Okay? And I happen to plot the gain plot below, underneath the phase plot. And then I'm sorry, I don't have any axis on the horizontal or the y-axis, but you can read it. So right now it says phase is negative 52 degrees, and the gain is 4.77. Okay, those are the red dots. When you look at these plots, okay, when you look at these plots, oh, I think my dot might have moved. Okay, so when you look at this plot, you see the 5 around 4. I can believe this is 4.77. About the dot, yeah, I think that definitely moved. Sorry. Okay, I'll fix that one later too. So I'm gonna start this. Okay, you watching? You see the color is changing when I hover. Okay, so this is a response of the mass, okay, when the base is moving. So this is a model of a car that's traveling on a road that has a harmonic shape. So you can see your output x of t grows, but it reaches a steady state response. Okay, where this amplitude is about 5 times exactly. It's a 4.77 times the base motion. Okay, the base amplitude is like only like let's say it's plus minus 1. Amplitude is 1. Okay, 1 something. Okay, and whatever it is, your output response will be about 4.77 times that. Okay, so let me pause. Let's look at the next slide. So next slide, oof, I already did that one. Okay, so oh, by the way, the same animation can be found in my web page. So there are other some random stuff in there too. So when you have, what's this? Did I just do that one? Yeah, I'm pretty sure I just did that one. Okay, so now let's look at the next one. So this is when R is 3. I'm thinking, why 3? Why 3? I'm sure I have a good reason for this. Okay, so let's try. I'm going to reset and 3 times. Okay, that means base frequency is about 3 times. So I think I'm going to have to reduce this. How about 1.5? And I can go to, ooh, this is going to take a while. Okay, I'm going to try to go to 4.5. 4.5. Here it is. Okay, so your base frequency is 4.5. So now this is a car model that's traveling faster. Okay. When you look at the gain plot, it's nearly 0. Okay, what's the actual number? It's 0.15. That means like 15%. Okay, so you have your output response is only 15% of your input in base motion, and then phase is nearly 180 degrees. So let's see. Let me see. It says 145 degrees. Let's look at this one. It's about, is it about 145 degrees? Oh, my dot moved. It should be right above 3. Okay, right above 3. So I'm gonna start the simulation. What do you see? I think there's a little change in response in the beginning. Okay, okay, so I can see multiple, I can see more than one frequency. Now it's purely going up and down, up and down, up and down. And can you see when your mass is going up, the ground is going down, right? When this green dot is moving up, it's kind of moving downward. So, so what do you see? So in this case, when the base frequency is a lot higher than the, 3 times higher than the natural frequency, you can see the output response is tiny, it's small. Okay, so I'm gonna pause and I'm gonna move this out of the way. Okay, here it is. Okay, so this is I guess this is the response plot with respect to the time. Okay, the blue one is the response and the white is the ground motion. Okay, it's just going up and down with a plus minus 1 amplitude. So let's see some questions. Let's see if you can answer this. The steady state response to the harmonic input oscillates at what frequency? Of course, at the input frequency. Okay. What I'm trying to say here is that your what was it? Your natural response, your natural frequencies, they will disappear. Okay. If you wait long enough. So second question, the steady state response of an asymptotically stable system oscillates at both damped natural frequency and the input frequency. Oh no, that would be, I mean, it's the same question as the first one. It's false. Why? Because um, your change in response oscillates at the damp at both. Okay, at both. Should I say both? Okay. The only time you see the damped natural frequency or the natural frequency damped natural frequency is in the beginning. Okay, when you can still see the change in response. So the third question, the input frequency is at which the steady state response is maximum is called okay, this one you may remember, you may not remember. It starts with R. It's the resonant frequency. The last question, at resonance in the absence of damping, the response grows. Ooh, you have to remember something from systems and vibes. Exponentially, quadratically, or linearly. If you remember, this grows linearly. You can actually see this pattern. Okay, see this pattern right here. Okay, when you see when the response grows, it grows kind of close to like a line. Okay, it's not exponential, definitely not. Okay, so maybe a line. Okay, a line. Okay, so you can tell when the R is almost equal to 1, okay, let's say it's 0.99, what will happen is that you have a longer period of growth. Okay, a longer period of growth, then it reaches a steady state and the response amplitude will be become constant. Okay, it will no longer grow at steady state. Okay, so now moving on to the base excited 2-degree freedom system. Okay, so this is the actual lab we have, and then what we have is the 90 degrees. Okay, so you're gonna have to rotate the bottom system by 90 degrees counterclockwise direction, and then we have two-story building model. So instead of having a regular spring, okay, coil spring, we have leaf springs. Okay, leaf springs at a flat flat plates that can bend. Okay, so this is the plate side is the you can see the plate if you view it from the side. So the reason I put it sideways because the mathematically, okay, equations of motion is exactly same as the one that we study um, in ME3333. Okay. So equation of motion. So I actually even drew the free body diagram of the two masses, and then these are the equations of motion. This is equation of motion number 1. This is equation of motion number 2. They're written in the matrix form. Why? I think I just like matrix form. You don't have to. Okay, you can just leave it at that. Okay. So how similar or dissimilar is a 2-degree freedom system from the single degree of freedom system that we just studied? The first of all, the number of natural frequencies is now you have 2. Instead of having 1, you have 2 natural frequencies. And for each natural frequency, the system has a unique shape of vibration. They're called the mode shape. In a steady state response, the harmonic input still oscillates at the input frequency. So whatever, if you shake the floor at 10 hertz, you'll see the response at 10 hertz in both masses, mass 1 and mass 2. The transfer functions are still a good way to represent the particular solution to any harmonic input. That's probably the fastest way to get to the particular solution or the steady state solution. So the current lab setup, okay, I rotated this 90 degrees so that you can see better. The mass 1 and mass 2 are the same, and K1 and K2 are the same. Okay? And Y sub T is a given harmonic motion which I have 100% control over. Okay, we have it's connected to the computer. All I have to do is just put in what kind of amplitude I want and what kind of frequency I want, and it will start shaking the table. So now, to figure out the natural mode of vibration, so you may remember this from Systems and Vive. This was the last test. If you had me for ME4333, the mode shapes and the natural frequencies are found using simply, that's the fastest way, using MATLAB. Okay? So right now I don't know the mass M and I don't know K. I'm gonna just lump it together with what is it called, eigenvalues. So this is my K matrix, 2, -1, -1, and 1. This is unique to what? To our system, with the mass being equal to each other and K being equal to each other. And then M is the identity matrix, 1, 0, 0, 1. Okay? And then if when you do the eigenvalue problem, you find this is your first mode shape, 0.5257 to 0.8507. This is first mode shape with eigenvalue, the first eigenvalue being the 0.382. The way I wrote this problem, your eigenvalue is the m over k times omega squared. That means your omega 1 is 0.618 times square root of k over m. The reason I'm not telling you what k and m are, actually I don't know. Okay, I don't know what they are. Okay, experimentally I measured the natural frequencies, and experimentally I know what omega 1 and omega 2 are. Okay, from there I just guessed what the k over m must be. Could it be 270 or 460? I can't remember. Okay, you're gonna have to go to the lab. Okay, it's in the worksheet. So let me tell you a little bit more about the mode shapes. So this is for the mass 1, first floor, and then this is for the second floor, 0.8507. What that means, okay, what that means is that when it's vibrating at the first mode, okay, so if you look at these numbers more carefully, take out your calculator, okay, so I want you to divide these two numbers by 0.5257. The first one will become 1, second one will become 1.618. Is that right? Okay. So to see that first mode shape, what you do is you release the two floors. Okay. The first floor at 1 unit to the right, and the second floor you pull the second floor to the right by 1.618 unit to the right. Okay. Whatever that unit is, it could be centimeter, 1 inch. Okay. And when you do that, you'll see a purely harmonic motion. Okay. Purely harmonic motion. So this is one instance, okay, of motion where the base is not moving. Right now this is a free vibration. Base is not moving. Mass 1 is pulled by 1 unit, and mass 2 is being pulled by 1.67 unit, and then it will sway. The whole thing will sway. The whole thing will, mass 1 and mass 2 will go to the right together, and then go to the left, go to the right and left. Okay, they're in phase with each other. Okay, when M1 is having a maximum, positive, right, maximum, and M2 is also having a maximum. Okay, so when you look at the period, okay, this should be 0.618 times square root of k over m. Okay, for the simulation, I can remember what I used for the k over m. The second mode of vibration, it can be simulated. Not simulate. You can actually excite this. You can actually do this in the lab too. So what I will do is I'll look at this number. Okay, this one has ratio of negative 1.618 to 1. Okay, so what I do is I pull the first mass by which one is first one? Okay, first mass by 1.6, red one, 1.618, and the mass 2 in the opposite direction by 1 unit to the left from the original. Okay, so original position was right above base. Okay, and I guess this this mark must be 2 units. So I move it to the left by 1 and mass 1 by 1.618 units to the right. Okay, then what you'll see is that you'll see mass 1, well, mass 1 is all the way to the right, mass 2 is all the way to the left, and they'll start oscillating, and then they're 180 degrees out of phase. Okay, you can see that from the time plot too. When red one is having a maximum, blue is having a minimum. Okay, it's on the other side. So now going back to the harmonically forced system. Okay, response. So this is not technically forced system. This is has a you have a prescribed input motion. Okay, the input is a motion, not force. So now going back to the original equation of motion, what I want to do is I want to find that, okay, how does the response vary as I change the base motion. Okay, and then base motion is will be a harmonic with a given amplitude with the frequency that I decide. So so let's see, and this is actually a pretty hard to do it by hand. Okay, so we can skip. Okay, skip. Um, Let me see. Yes, let's start from here. Okay, so this one we can do this by just setting the damping equal to 0. We can actually do this by hand. So from the matrix form, you don't even have to use a matrix form. What I want to do is just set c is equal to 0, the zeta is equal to 0. Okay, zeta is equal to 0, and you get the following equation. Okay, in Laplace transform, you took a Laplace transform and then set c is equal to 0. Then what's your goal? I want to find the transfer function. What transfer function? It will be x1 divided by y and x2 divided by y. Okay, how do we do that? You have to solve two simultaneous equations. So this time, I think in my class I use the Cramer's rule all the time, but this time, don't ask me why I decided to do it. This time I actually inverted the matrix coefficient, the coefficient matrix. Okay, so I inverted this whole matrix and multiply by the right hand side. Okay, and I'll just give you the result. So this is what the result will look like. So this is actually quite annoying because I'm not giving you what m over k is. Okay, so your first transfer function looks like this, and then the blue thing is your second transfer function. First one is for the first mass, and second is for the second mass, and and then you'll note, okay, they have the same denominator, and there's a certain value of omega that will make the denominator equals 0. Okay, and that value is when omega squared is equal to 0.618. Oh, that's a very popular number for this problem. It's times square root of k over m, and 1.618 times square root of k over m. Okay, so now we're gonna use something called a non-dimensional frequency called eta that looks like n, eta. So eta 1. Okay, instead of keep saying, oh, first natural frequency is 0.618 times the square root of k over m, I'm going to say first natural frequency, non-dimensional natural frequency is 0.618. Okay, so your eta is omega divided by that thing, okay, square root of k over m. Okay, so your Bode plots. Okay, so I went ahead with the Bode plots. So I replaced m times omega squared divided by k as eta squared. Okay, similarly, divide because I want to plot the Bode plot. Bode plot is in S domain, right? You need to find the coefficient of the transfer function in the S domain. So I denoted the m s squared divided by k as capital S squared, so that way I can just have numbers. So I plotted the Bode plots. Actually, I didn't plot this one. This is from your worksheet. So this is actually I wish I could change the vertical range. So those are like, there are 4 plots in one. Okay, the first one is a magnitude plot for the mass 1 in black and mass 2 in blue. Okay, don't mind the red lines yet. Okay, don't worry about that one. And phase plot is again same thing, black for the first floor mass 1 and the blue for the mass 2. Okay, and then x-axis in terms of eta. So this, and it not only it's a logarithmic plot. So eta equals to, that's the first natural frequency of eta equal to 0.618 is around here. You can see this is a zero point 0.1, zero point 0.2, 0.3, 0.3, 4, 5, 6. It's around there. And then second natural frequency is this is 1, this is 2, between 1 and 2, 1.618. Okay, so now I want to show you, okay, before I discuss this, okay, I want to show you, okay, I want to show you um, uh, the, the body plots that I generated, and then I kind of chopped off the y-axis. I changed the range of the y-axis. Here it goes to 200 and negative 400. I didn't like that at all, so I changed to negative 40 to 60. I mean, when zeta is equal to 0, they blow up. Okay, so the reason why you don't see that it's going to infinity, okay, these two peaks, okay, they are the two natural frequencies, and then they should blow up. The reason why you don't see is it's because it's MATLAB and I'm sampling at, like, every point, I don't know, let's say 0.1 eta, um, and then I don't actually never have infinity, okay, because I'm not really sampling right at the natural frequency. Um, so so I wanted to show you, this is the first plot is same as this plot, okay, with the y-axis um, changed, range of the y-axis changed, and the x-axis in my plot, it only goes up to 2. This one goes up to 10. Okay, I just chopped it off right here. Okay, I just zoomed into the more interesting area. So now as you increase damping, so this is all done in MATLAB. There's no way I was gonna do this in by hand. Okay, remember I was generating a matrix, I was solving two simultaneous equations. I mean, they become very complicated with the damping. So anyway, so when the zeta is equal to 0.01, as I slowly increase the zeta, what happens? Okay, your peaks are not as pronounced. Okay, and when zeta is equal to 2, that's definitely overdamped system. What do you see? You see it's like a flat line. Okay, okay, not flat line, it's okay, decreasing line. Okay, so you don't see the peaks anymore. Okay, so what happens when you increase damping? Well, the natural frequencies just having resonance is just not as traumatic as you think it is. Okay, even at 20% damping, it's not so bad. Okay, so now let me point out one more thing. Okay, what does it mean to have a negative infinite decibels? Okay, so let's see, negative infinite decibels divided by 20 decibels, that's negative infinity still, and raise it 10 to the negative infinity, that is what is that number? Okay, I'm trying to change this number, negative 40 decibels, let's say, okay, or negative very large decibels, into a pure ratio. Okay, so you have 10 to the negative infinity, and that's definitely not infinity or negative infinity, that's 0. Okay, nearly 0. So we see something really interesting. Okay, really interesting right here. Okay, I'm gonna go back to previous plot. Okay, so you see something really interesting when eta, okay, non-dimensional frequency is equal to square root of k over m. That's the original, that's the natural frequency that the system would have had if it was just one mass in a one spring system. So at that frequency, your mass 1, the first floor, comes to a stop. Okay, it has no amplitude. Okay, so this is also called a zero frequency, because that's the frequency at which the first floor will stop moving. Okay, so I divided this region into 4 regions, A, B, C, D. A's before when the forcing frequency is below the natural frequency. Second region is between, okay, between the first and the zero frequency, and C and D and so on. Okay, so now let's examine region A. I think I might have put the C equal to 0 for the simulation. So region A, this is when the natural frequency is I'm sorry, the forcing input frequency is below the natural frequency. Then you can see the phase angle are zeros. Okay, with respect to what? 0 phase angle of the input. So what you see is when the first floor, okay, first floor is having a peak all the way to the right, now base is moving, okay, to the right. Mass 1 and mass 2, they all move to the right. Okay, it's as if the base is carrying all masses to slowly, okay, to the right and left and right and left. Okay, so if the base moves to the right, so the other two masses. Okay? So that kind of makes sense, right? It should just the base should just carry the whole thing with it when it's moving slowly. So right, so when you do this in the lab, there is some damping. So you just wait long enough. Right now it's after 200 seconds, and I still see. I mean, I right now, I mean, in my simulation, I set the damping equals to zero, so my transient response is not really dying easily. So now let's go to the next plot. So this is when you have input frequency that's at nearly at the first natural frequency. Okay, eta is equal to zero point 0.6, a little bit to the left of it. Okay, and and then you can see the amplitude is growing, growing, growing. I mean, I chopped it off too early to see how much it grows, but imagine quite a bit. Okay, so this is when you have what's called near resonance. Okay, so now next one, when you have the input frequency between the first and zero frequency. So when you look at the phase angle, okay, when you look at the phase angle, they're both out of phase, 180 degrees out of phase with respect to the input. Remember, input has a zero phase angle. Okay, so mass 1 and mass 2 has a negative 180 degrees phase angle. That means whenever the base is going to the right, your two masses are going to the left. Okay, so point A was still too close to eta equal to zero point 0.6, so you can see the magnification of like almost 4. Okay, so here you can tell when the base, okay, when the base isn't at the left, okay, leftmost place, your mass 1 and mass 2 are at the rightmost place. And you can see the mass 2 has a higher amplitude, and you can see that from the amplitude plot, okay, the magnitude plot right here, or gain plot. So the next one is that region, the C, when the input frequency is between the first and the second, I'm sorry, the zero frequency and the second natural frequency. So I had to zoom in a little bit. Okay, this one I actually didn't put in the damping. I should have done that from earlier on too. So that way the transient response will die out. You don't see that anymore. Okay, so this is time just near the like a little like last 50 seconds of this time history. So here, what does it say? When you look at the phase plot, your mass 1, the first floor, is in phase with the input, the base, but the mass 2 is out of phase. Okay? So what does that mean? When the base moves to the right, so that's the first floor, which is in red. Okay? But the second floor is goes to the left. Okay? Just looking at the phase, you can see roughly what the forcing frequency is. And of course, if you want to know the forcing frequency, I'll just count. I'll just look at the time for that. I'll just look at the period, peak to peak distance. Yeah, and then figure out what the period is, and then invert it and get the frequency in hertz and change to radians per second. So, region 4, this is a near 1.7. Okay, 1.7. Again, you see beating. I want to show you. Okay, I want to show you how the response grows. Okay, why? Because you're very near the second natural frequency. Okay, it happens to both. Okay, it happens both mass 1 and mass 2. And then here it says mass 2 and the ground, the base, are in phase because 360 is negative 360 same as 0 degrees. And the mass 1, only mass 1, it is out of phase with the other two. So when the base goes to the right, the first floor goes to the left, and the second floor goes to the right. Okay? This is probably the most dramatic thing you can see in the lab. Okay. D, this is when it's far out. So you can see clearly when the base goes to the right, mass 1 goes to the left, okay? And then mass 2 nearly in phase with the base. Okay? So when you can actually see it, it's quite dramatic. Okay? So conclusion, what did we learn? We saw two natural mode of vibration for the two-story building. Okay, when even the base is not moving, you can see there are two distinct motions with the two natural frequencies. Each natural frequency, one natural frequency associated with each one shape, mode shape. The steady-state response to harmonic excitation can be found using Bode plots. Okay, you don't have to experiment all the time. You can just plot them using MATLAB. And the Bode plots can predict the amplitude and the phase of the steady-state response to harmonic excitation. And then this is all, when I say steady-state response, I want you to remember these are really particular solutions. We're assuming the homogeneous solution all disappear because it's an asymptotically stable system. Why? Because we have damping. Okay, and then this is the end of the lecture for the lab 7. Okay, thank you.